Recordings rolling. It's Thursday, January 8th. Going to be doing rotational inertia lab today. You guys, well, if you sit in class, you guys get this set in front of you. I'm going to get a few volunteers in a few minutes to. Oh. Here's the things first. All right, okay, and you guys have this lab page. You're gonna keep data on, right, and then right, guys, on the back of this page, do you guys see your 5-part AP style write up? Right. So I'm gonna have you guys do one of these also. Right. If you don't finish this by the end of class, I'll just have you turn in tomorrow. But we should get the data in class. We're gonna do this together as a class, just for a lot of reasons. It's better to do this lab this way. Okay. All right. Now, tomorrow, a couple things going on. Well, in class, I'll just do puzzles with you guys. I've been trying to get towards angular momentum. Now, you guys had just started it at the end of yesterday. My other class, I didn't get angular momentum, so I'm just going to push that off a few days. We'll just focus on rotational inertia and torque, right? Which by AP's book is Unit 5. Okay. And then another event going on tomorrow is called Tied Together. Here, I'll show you guys the same email I got, so we're all reading the same thing here. Okay, so it says, hello, Hawks. This Friday will be the Tied Together event at VHS. Students will be released from each class by announcement after attendance is taken. We'll start with 9th grade and work our way towards seniors' 4th period. Since 4th period is lunch, have all seniors go to the gym the first half of class on Friday only, and then go to class for attendance. And then go to B lunch. Please tell them about this now so they know what to do on Friday. To clarify, all seniors go straight to the gym for Tied Together on Friday and 4th, and then go to attendance, and then go to B lunch. Okay. All right. If you have any questions, we check. All right. So that's going on tomorrow. They'll make some announcements. So just listen for the announcements and just put them in. Okay. Right. AP Classroom. Let's look at AP Classroom here. All right. So you guys know I had opened Unit 5 and 6. Now, guys, Unit 5, the due date's the same as it was before, which is Monday. Right, you guys see Monday the 12th? Can you guys have Unit 5 done by the time you guys come to school on Monday? Right, so that, of course, we'll go over the answers then. Right. Unit 6, I bumped back a few days because yeah, we'll need at least a few more days to for that one, right? But this one's still due Monday the 12th, right? I was reading a bunch of these questions. I think you guys will be able to answer these. So, guys, in Unit 5, quick recap. There's rotational kinematic motion. You guys remember like turntable type motion, right? Kinematic formulas and stuff. There's torque and there's rotational inertia. That's all in Unit 5. And then Unit 6 involves angular momentum, which I'm trying to get towards. Okay? All right. Any questions so far about anything? One more thing right before we get started on this lab. Yesterday I was walking through some puzzles with you guys and I realized that one of my posters has a mistake on it. So under thumbnail notes, here, we're going to do a correction here. We're going to flip to the purple banners, of course, which we're on. Right, purple banners right here. I feel like I think it's on this side. It's the one with the ladder. You guys see this ladder right here? Right, see the ladder? You guys remember yesterday we solved the ladder puzzle in class? Right. It's the one that says this fraction is equal to tan theta. That is actually not true. So just scratch that out. You guys see I'm scratching out this fraction is equal to tan theta? Okay. And so, oops. So, correction. All right, so everybody's got that corrected in their thumbnails? Okay, so the ladder, this fraction is tan theta, that is actually not true at all. All right, so that updated. All right, shuffle these up. Right. So, you guys remember rotational inertia is something about mr squared. Well, for a point mass, it's mr squared. You guys remember that? Okay. Now, if you have a rigidly rotating object, I mean, some of these objects have been worked out with calculus. Okay, great. So, like, spherical shell could be 2/3 mr squared and so on. Okay. But what you guys are seeing in front of the class right now is this weird T-pipe shape. You guys see this? Okay. And it's free to rotate about the central axis. You guys see how I'm rotating it? You guys see that? Okay. Now, there's a little bit of friction that'll show up by the end of the lab. That's okay. Right? But it is low friction, but it's not zero friction exactly. Okay. And I have a box of lab weights. I have a meter stick right here set up. Looks like the height that it can fall is about 70 centimeters or so, about 70 centimeters that can fall to get to the floor. Okay, and there's a stopwatch out there. Okay, you guys saw that? And do you guys think that if here, guys, what if I took these arms off right here? If I take these arms off, what you guys imagine? Do you think there's a lot or very little rotational inertia in the central pipe? Guys, it's a very easy or very hard to change the state of motion. Very, very easy. There's hardly any rotational inertia at all. You guys see that? And just flutter it back and forth. Here. But once they pop these arms on, ooh, do you think this feels entirely different from before? Yeah, what do you think just happened to the rotational inertia now that I put the arms on? Yeah, it increased a lot. Hey, I wonder if we can quantify how many kilogram meters squared, because that would be the unit for rotational inertia, right? Mass in kilograms, distance could be in meters, kilogram meter squared could be the unit. Is this right here. Okay. Right, so I want to do a couple of perspectives on it. One perspective is, well, you guys said the central pipe without the arms probably has just a tiny, tiny amount. So when I pop these arms on, probably most of the rotational inertia is in the arms. Do you guys think? Okay. How many of you guys think that this right here looks a lot like this right here? You guys think that would be true? Yeah. Right. So I'm going to get a few volunteers. A couple volunteers. What I want you guys to do is, do you guys see that triple beam balance back there? Right. So I put a bunch of other parts back there because I have a few of these sets. Right. How do you guys get the mass of these arms and also the length using a meter stick? Right. Well, okay, you might have to show this meter stick up here. When I got it. Right. Okay. And then we'll get an estimate of what the rotational inertia could be just from these arms. Probably fairly representative of the voltage. Right. Right. So who wants to volunteer to do that to get the mass? Right. Yeah. So Nathaniel. Anybody want to help Nathaniel? Well, I'll tell you what, if you want to help Nathaniel, here, there's a tripling beam balance right there. All the materials back there. Okay. So here, while he's getting that, here I need a couple volunteers to run this, and I'm just gonna help you guys keep track of it. Okay. Guys, who wants to be up here operating this? Need two volunteers. Two volunteers. Right. So Justin and who else? Justin and how about Logan is volunteering? All right, so Logan. All right. I guess I don't know. What are we doing now? But yeah, just you guys up here. Here. Yeah, thanks guys. It's gonna go man. I got this. Okay, so here's the poster version, but here's you guys' actual page. So yeah, with you guys here. Oh, and I guess Lily and Austin, can you guys help keep track of their data?
Yeah, come over here.
Just
stay over
keep
there.
track of their data.
Do my work for me.
Because yeah. All right. All right. So what we got here? Ooh, we got to get what's the radius of this central pipe? Okay. You guys see on this postcard it's marked R. Okay. So you guys have a meter stick or a ruler. Okay. Can you guys get figure out what is not the diameter but the radius? Or I guess you could get the diameter divided by 2. You could do that. Right. So what are we looking at there? What? Okay, so diameters. Okay, guys, if the diameter is, if they're calling the diameter about 3 centimeters, if that's true, what's the radius?
1.5.
1.5? So go ahead and let's call the radius. Oh, I did put it in meters. So how many meters would that be?
Point oh.
Yeah, 0.015. You guys got that? Okay. And that's going to be true all the way down.
I think
So just all in meters. 0.015, 0.015. Okay. Right. Then what we do is we're gonna put different masses right here, hang different masses, and let this fall. Right. Here, Logan, you want the stopwatch? Right. So Logan's gonna take care of the stopwatch. Justin's gonna hang on the masses. Okay. So let's start with see those 2 right there? That's 150 grams. Put both of those on there. Okay. So it's kind of the minimum to get it going. Okay. So to see a loop, you can hang those on.
Yeah.
So we're going to call this 0.15 kilograms.
Or I'll just leave it.
Okay.
Okay, yeah.
Okay. All right. Now, Justin, what you're gonna do is also measure this drop height to the floor. So what's the difference between the weights and the floor?
Is it the bottom of the last weight?
Huh?
Bottom of the last weight?
Yeah.
Okay. So yeah.
61.
61 centimeters. Okay. So yeah, 61 centimeters. How many meters would that be? 0.61. Okay. That's probably gonna be true for all these what's called 0.61 meter. Okay. Right. We gotta figure out how much time it's gonna take. Alright, so as soon as you let this go, Logan time how much time it takes for this to reach the floor. Right, you guys ready? Ready?
Like, what is it set?
Go. It didn't move. It didn't. Oh, it is go. It is go.
That
I don't think
that not take it.
Alright.
Okay.
Yeah, now we restart.
Oh, okay. The string got caught under your hand. Okay.
I don't think that big.
Yeah, the string got cut under your hand.
Okay.
We got 297 of the two arms, and then if you include like the thing, it's like
Right. Yeah. Actually, tell you what. Let's take care of that first. Right. So while just a Logan or getting set up right there. So you got how much mass for each arm?
each arm is 148.5.
Mass of the arm is sorry, what did you say?
I'm sorry, 148.5.
148.5 grams. Right. Okay. So guys, one of these arms is that much. Okay. So together, what would you say?
97.
Okay, so you found for this entire top beam would be just double that pretty much?
Yeah.
Okay, yeah, it's probably pretty close to it. Okay. So the mass of two arms would, sorry, what was the number?
297.
297 grams. Okay, yeah, that sounds about right. Okay. Now, if we're putting everything in base SI units, that would be how many kilograms? 0.297 kilograms. Okay. Okay. So that's for this entire top beam right here. Okay, that beam. Okay. Which looks a lot like this. Okay. Oh, and what meters? Actually, let's here. You guys got meter stick right there. Okay. What's the distance from end to end with the meter stick? Yeah, from end to end. What's the total distance right there?
Which is more than 1 meter. It's gonna be more than 1. I don't know. At least 1 meter.
Okay.
No. Then goes to 7. Actually, not 27.
27? Okay, so 127.
And
So 127 centimeters. Okay. So the length of two arms is 127 centimeters, or 1.27 meters. Right, is that true? Okay. So we're looking at this mass, this length, that it can feed into this expression right here. Is that true? Is that? Okay. So I think that the inertia, the rotational inertia of the system is approximately 112 ml squared, which is 112. Here's your mass, 0.297 kilograms. Here's your length, 1.27 meters. Gonna square that. Okay, we're gonna get a number out of this. So it's 1/2 0.297, 1.27 squared. All right, looking at yeah.
What did you? How did you get it?
Oh yeah, 12.
Okay.
Oops. 1 over 12. Okay. 0.0399. Well, we're probably rounding a little bit anyway. Can I say maybe 0.04? Okay. Maybe kilogram meter squared. Okay. Now that's one technique of finding the rotational inertia.
Okay.
Okay. Which is to find the masses and the lengths and pop into this expression and find it that way. Okay. But what Justin and Logan are going to do is do this empirically, okay, and we'll also get the same idea from a completely different method. Okay. All right.
Are you ready?
All right, guys ready?
Go.
Reasonable.
Ready, Logan?
Go. It's going. It's going. This is true. It's so wow. This is about to be so epic.
So 36.7 seconds. Okay. Now, what you can do is you can grab the central axis and you can spin it. Yeah, and it'll rewind the whole thing. Just go rewind, rewind. Okay. Sure, guys. Watch this little trick.
Oh no, I know. Oh, some.
There you go.
We lost the win. Lost the win.
On the way, we lost the win.
Okay. So you guys know when you do your AP style write up, you want to mention take 3 trials per independent variable and take an average. Okay, so this is set up this way, right? Okay. So we're not actually gonna change the masses until we get down here, and it looks like we'll have 1, 2, 3, 4, 5 different masses we're gonna throw on there. Okay, but here, we're gonna do a rerun with the 150 gram right here. All right, you guys ready?
Yeah, it's like get this back. I got this. Yeah. Gonna make sure it's like yeah. Just gonna make sure it's also there one. We should do it there. Or no. Take your time. Hurry up. You got this. Might have to rewind it back a little more. Rewind it back more. Oh, no,
You got it's like wait.
I need to like.
Raise that.
That's not I've got first.
I'm doing. I don't know dog.
Okay, it's about ready. Ready, set, go.
That one's rare.
It helps. Because they go about 37 seconds.
I can think of about 36 seconds.
No, it was 37 seconds.
36.
It was 36.7. There's actually
they get caught.
Yeah, it's get caught. Okay, well, up to
Oh, we're moving.
This is why we did it.
Gonna take more. 40.37. So
40.4. All right. You know what? Since that's a really small weight, it's taking a while. Let's go to the next one. We'll just do 2 on that one. So yeah, let's go to 200 grams, which is 0.20 kilograms, which is just one of those medium-sized lab weights right there. All right.
Okay, this is I know. This one's got 60.
Okay. So 0.60 meters.
Yeah.
This was good.
It's just so fast.
It's like that watermelon stuff. Very, very.
28.7. All right. Let's do a rewind and take 2 on the 200 grams.
Oh, we're only doing general. It's rewind time. Alright. What takes it? I did get hit in the head already. I know, we saw. Ready? Set. Yeah. Don't worry about
Alright, so you guys, everybody else in class, if you're really engaged with what's going on, then that's perfectly fine. If you want, you could get a head start on some of these on the bat. Right? Like you guys know the question, we're trying to find the rotational inertia system. So what is the rotational inertia system? Right. What measuring equipment are Justin Logan using? How would you describe the procedure? All right, so how many seconds?
28.34.
28.34? 28.3. Yeah. All right. Good. Yeah, let's go ahead and hop on to the next one. All right, let's do 300 grams. We'll call it 0.30 kilograms. So is there a 200 gram and a 100 gram? Yeah, okay, that's 200. That one's down there is 100. Yeah.
There's one right, yeah.
All right. So together that'll make 300 grams.
You can do my test. Like we did.
Okay, bring it up a little one, gang.
Oh, yeah.
Oh, back again. About 60.
All right, that's 0.60 meters.
Ready?
Okay.
Guys, watch.
It's moving fast. Oh. It's okay. Oh.
21.6. Back in. Okay. Take 2.
No.
60% error.
You're getting close.
So, we're upside down. I feel like it's negative math.
Okay. Ready?
Yeah, all of them. Yeah. 21.
21 what?
21 seconds.
I mean,
21
do it.
Yeah, okay, 21 what? All right.
What next?
Yeah, but let's go 400 grams. So 0.4 kilograms.
Yeah, there's. Energy, your problem. It's concentrate. Oh no, it's still concentrate.
It's all. Still in the back.
Okay, I do like.
Very weird.
Yeah.
I think I got it.
No, it's still. Red dot. We got. We're professionals. It's like it's on their way. Yeah.
No, hasn't been. There's totally. I know it's.
A little bit. Yeah, I'm watching.
Oh no, the string broke.
Screen broke, Mr. Day. We have more try.
Well, where is it?
I didn't do none.
Yeah, they done.
It's like, you know, I heard like, it's like, this is all stuff out there in the country, but they most people. Right? Well, you know, okay, I was raised, well, I live it's okay with your question, that's just. Right, I don't have to. Yeah.
So 0.58 meters.
I'm ready.
Set.
Yeah. It's gonna happen pretty fast. First period, bro. Oh, it's kind of like rotating here, but then go back. It's not before it goes one color.
And
17.7.
this is
17.7 seconds. And take two.
Oh, you're right.
This you just gotta do, I don't know. It's about how you carry yourself or something. That's a story.
Yeah, that's not just where I gotta finish with it.
okay.
So, I carry you. So, okay, ready? Yeah.
And they really good. Animations and things.
Animations in the last 6 years old.
Oh,
17.
you're in. Oh, 17.3. All right, let's go into 500 grams.
500.
That'd be 5 kilograms.
Oh, that's
Right.
not yeah.
That's like, you know, I could went into one piece.
Except the first so dull. I like the same amount. Yeah, so it's at the end.
R1 Park is still out by Marty. It really is. R1 Park is like not like a bunch.
Okay.
Leech is better.
Out.
0.6.
0.60.
Ready?
And
you get a match.
Go down.
Skyfield is very slow. Bro. 15.
you're not a
One more.
But the ending is
At least 10 grams. We're here for like 6 hours.
We're not here for that.
really speaking.
Put one Justin on that. See what happens.
No, we mean the opposite direction.
So many people. But I'll get that.
Yeah, my.
We went so fast, we ended up at
I got a lot of it.
yeah, the wavelength bears were
15 point standard.
All right. So, let's say we have enough data here. Now, if you're doing an AP write-up, you probably want to mention doing at least 3 trials per independent variable. We'll just do 2 because we got so much class time. But yeah, all right. So Justin Logan got some good data. So what are you going to do with this? So you guys probably also see the first 4 columns are marked measure, 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 right? And everything after that, there's some little math expression there. It tells you how to calculate the rest of this. Right? I'll walk you guys through it. So, you guys remember our end goal is to figure out what's the rotational inertia. Right? Hopefully you guys already know. Here, if you look on the backside of this question, I say, what is the rotational inertia? Whoops. Yeah. Inertia of the pipe system. But I can't just say that because
You can't just say.
you guys see that all these there's some axis that's defined that it's rotating about. Like this and this look like the same shape, but they're rotating about different axes, so there's different rotational inertia. So I have to say about the central vertical axis. Right. And of course, you'd have to refer to a picture or something, but I think that should be sufficient, right? Ooh, guys, what measuring tools do you think might be involved here?
Ruler.
Yeah. Yeah, ruler or meter stick is either one's okay. Yeah, stopwatch. Ooh, yeah. Right. That's probably a good one to click to. Okay, triple beam balance. Right. Or you could say a scale. Right. Or oftentimes, if AP provides you the lab weeks ahead of time, says, oh, it has a number stamped in it, they don't necessarily require this, so they're not looking for it necessarily. Right. Definitely the meter stick and the stopwatch. Right. Yeah, it's probably a good idea to put that. Okay. All right, your scale. All right.
Well, so
Right. Okay. Yeah. As much as I want to help you guys out with the procedure. Okay. I'm gonna leave this to you guys to use your imagination. Think. Okay. Well, if I was taking the AP exam, what it is, and normally they're looking for somewhere between like 4, 5, 6, 7 steps. Usually no more than 7 steps, but if you have like 5 steps in it, like what did you do with these tools? So you want to mention each of these tools. I use this tool to measure this. This tool to measure this. This tool to measure this. Okay. And that's all you're doing. So everything that Justin and Logan did so far, I use this tool to measure this. This tool to measure this. That's really all that goes here. Also, guys, we got to mention doing. Okay, so briefly describe the setup. Okay, so you have the pipe system set up. Okay. Got a string, got a pulley, got some weights. Okay. Which measuring tool do you measure which variable? Okay. Guys, what variable did we change? Did Justin Logan change?
the weight.
Yeah, the weights. The weights. Right, the weights and newtons. Those were changing. And what was responding to that? Yeah, how much time it took. Okay. And it was pretty much a set distance, somewhere between 60 and 70 centimeters. It varied a little bit. That was approximately. So I think you can call the drop distance pretty much control, gravity field control, all that stuff. Okay. And then you guys always mention this detail: multiple trials to reduce experimental uncertainty. That's always a point there supporting. Okay. And we're about to go into analysis, which is how we're going to crunch this data and make a graph, and then how we're going to interpret that graph to eventually lead to conclusion, which answers the question: what's rotational inertia? Okay. So let's go here. Right, next. Yeah. Okay. Now, guys, ideally you'd be able to come up with the rest of this from scratch, but I'm just going to go step by step. So have your mind come on. We're going to find what's the linear acceleration. So, guys, what's the linear acceleration of this falling straight down?
9.8 meters.
Well, guys, it would be 9.8 meters per square if you dropped it and was in free fall.
Oh yeah.
But
No.
it's not quite a free fall. Here, we can use this one right here.
Yeah.
And how can we simplify this? Which term can we get rid of? Yeah, V not T, because that's just zero anyway, right? Drop the rest. Can you guys say the height drop equal to 1/2 A fall times squared? Can you see that? Okay. Here, everybody right now do some algebra. Solve for A. What do you get? Do a little algebra.
I guess
Just a couple of algebra steps. And what'd you guys get? Yeah, 2 times the drop distance over time squared. Yeah. Alright, so everybody got that? Yeah. Okay. And that is exactly what this says right here. Yes, yeah? Right. So let's go ahead and get the linear acceleration. So 2 times this drop distance in meters divided by the fall time and seconds squared. Okay. Okay.
I can do it, guys. 0.00.
Yeah, you know what? I got a tiny number.
Yeah.
Okay, I did it right.
How did I do this last year? I've been using this table for years. How have I been doing Here, guys, let's do this. Let's in the heading, let's put times 10 to the what? 1, 2, 3, 4, 5. Can I do 10 to the -5? Is that okay? Okay. Say times 10 to the -5. So whatever number we actually write here, can you scroll the decimal back 5 places? Because the acceleration is so tiny, right? So 1, 2, 3, 4, 5. I'm going to call this approximately 90.6 or 91. Okay. Okay. Next one. If I put in 40.4 here, I'm going to get 1, 2, 3, 4, 5. 74.7. Right. So 75, 90, somewhere in there. Okay. Yeah, and here I'm gonna go all the way down and do the rest of these. 2 times the drop distance divided by the fall time squared. Okay. 1, 2, 3, 4, 5. I'll cause 146.
Yeah, I don't know.
150.
It takes so much time. It doesn't fun.
Then
Like I can do it.
1, 2, 3, 5, 257.
Nice. Do acceleration. You can pick
270.
147. No, wait, hold on.
Yeah. Okay. Chris, you guys should be getting the same numbers I'm getting, of course, because I'm just plugging in the calculator. Okay. These are all, of course, 10 to the -5 seconds.
I'm getting this here.
Or, sorry, meters per second squared. Right. 0.58. 1, 2, 3, 4, 5, 370.
We just gotta put it over here. Over the issue.
388.
No, we should. Yeah, that's it. You must have back here.
10 to -5.
Oh my god.
And then,
Yeah, you need more. You need
I'm just gonna drink the rest of it.
I actually know.
got 513.
Well, what you copy?
And
I have no idea what that means.
487. All right. So yeah, it looks like the heavier the weight, the more the acceleration. That kind of makes sense, right?
Paul,
Next column. Okay. Now, guys, this one. It's a little bit of technicality that I've seen sometimes they can even get through it. But guys, the tension of the strings. Here, guys. All right, are you guys ready for a really nuanced question?
yeah.
The tension of the string, is it exactly equal to this weight or a little more or a little less? Little less? Right. How many guys think a little less? Yeah. I agree with that. You guys remember elevator physics?
Yeah.
If there's an upward accelerating elevator, the tension of the cable has to be more than the weight. If there's a downward accelerating elevator, the tension is a little bit less than the weight. Right. And it comes out to this expression here. Here's the derivation for upward accelerating, but if you have a downward accelerating, you just double some variables around and it looks like that. Okay. Guys, you should be able to do these type derivations by the time you get to the AP exam. Okay. But since we got so much class time, I'm just gonna plant that idea and we're just gonna use this and keep going.
Decelerate.
And so it says m times g minus a. So I'm gonna take the mass 0.15 kilograms. And then G, here I'm going to use G equals 9.8 meters per second squared. We'll do that today. Okay. Now, kids, this is going to be a really subtle effect because the acceleration was so tiny. In fact, guys, if you kind of ignore that, you just said the weight is equal to, or the tension is equal to mg, it would probably give you okay results. But we're going to do something. So minus, and then 98.6 times 10 to the minus 5. Right. So 1.47, yeah, whatever. And then 1.47. 1.47. Okay.
It's the same.
1.8. I'm still calling on
Like it's the same.
Yeah. I got one. It's
Oh, four, he's subtracting the linear acceleration.
Just don't
So small.
It's more talking.
Clearly has too much coffee.
Flying back there and. No, it's just you're subtracting the linear acceleration from the.
It's good. It's satisfying.
Okay. Alright, so I got all the tensions. Yeah, it looks like it kind of rounds to the weight anyway, so whatever. Alright, you guys up where I am? Okay, next column. Now we have the linear acceleration, we have the tension. What I'd really like to know is something about angular acceleration. Okay, how much because this was speeding up spinning, right? Now I put omega here for angular velocity, but really it would be accelerating, wouldn't it? I could put alpha there. I could put it there. And this is gonna eventually connect to this. So here guys, if you look at this picture, isn't this string tension at this small radial distance causing a torque? And that torque is resulting in, well, something to do with the angular acceleration. Now there's a little friction, but we'll look at that later. Okay, so I need to know the angular acceleration.
Right.
And here we go. So now guys, could this circle be a cross section of that central pipe? There's just a few centimeters in diameter. You guys remember that? Okay, so if you zoom way in, okay, and maybe your string is like right here, and this is the radius of that central pipe. Okay. And here's the connection between the linear acceleration we just found and the associated angular acceleration. Guys, how do you solve for alpha?
A divided by R.
A divided by R. You guys see that? A over R. Solve it. Which is exactly what this says right here. A over R. Get that? It's gonna take this A, which is 90.
Oh no, it won't be the big number.
Divided by this radius.
I already beat the George.
Getting 0.060. Now it's radians per second squared. And I gave you the unit too. Okay. You guys, if I did not give you this table, then you would know that this would be in radians per second squared anyway. Because angular acceleration.
That's really close for us.
Yeah. Okay.
I wonder what this is. Far back, bro.
Yeah.
I can't reach that.
Yeah. 0.097. No. 0.100.
0.171. Oh wait. He didn't even take it.
You guys are gonna get like a 700. 600 point curve. Dude, I'm getting 700 for that. 53.
Yeah.
That's
0.0.
Yeah.
Your point is
Yeah. Oh yeah, absolutely.
Alright, so now I have all the eagle accelerations.
We'll all be crying. Wait, so that means all of them.
Okay, and report. Okay, now we're gonna use this version right here. So our cross that. Now the radius we got right here as 0.015 meter. There's the radius. And we're gonna cross that with this tension right here. This tension. Well, let's put it that way. 1.47.
No, not 5.
Alright, so I'm getting 0.022.
I could.
And then the same there. Okay.
We got this data. Just know. We together got this data. Easy by around there. That's not very fair.
Yeah, when it broke on your side, you guys just like Oh,
On the desk right now.
I mean, I just.
Yeah, wait.
They were doing
Okay. Guys, we only got about a minute till the bell, so we're gonna have to finish this tomorrow. But I'll help you guys out. So tomorrow in class together, we'll put together this graph. We'll come up with this answer, and then don't forget, beginning of class, we had a different way to get rotational inertia. We came with this number. So I wonder how close this is going to be to this. Should be fairly close, but we're going to find out. And then you guys remember also the AP write up on the back and leave it to you guys. Okay, no, I'm going to grade it. But,
Oh.
to you guys soon.
No,